Welcome to another video from explainingcomputers.com. This time it's my 9th annual review of developments in quantum computing. Whilst traditional computers process data using binary digits or bits, quantum computers use quantum bits or qubits, which can exist in a superposition of multiple states, and this can allow quantum computers to perform massively parallel computation. Qubits may be created using a variety of techniques, with different pioneers favouring different technologies, as we'll see across this video. 2025 is the International Year of Quantum Science and Technology, which is focusing a spotlight on quantum computing. Already, over $1 billion a year is being invested in quantum computing hardware and software. And the Quantum Insider's 2024 annual report predicts that the quantum computing vendor marketplace will be worth $5 billion a year by 2030. Quantum computing is also starting to have implications for computing more generally. For example, in November 2024, the US National Institute of Standards and Technology, or NIST, published a report on the required transition to post-quantum cryptography. This is the detailed technical document that, like all other references, I'll link in the video description. But the key takeaway is that many current standards for digital signatures and cryptography keys are going to be deprecated by 2030 and disallowed after 2035 due to their potential to be compromised by future quantum computers. Right now, quantum computing remains in the research and development phase. But over the past 12 months, many pioneers have reported important innovations. Sadly, covering all of them would make this video far too long. So let's focus on 5 key developments that have really caught my attention. In December 2024, Google announced a new quantum processor called Willow. This contains 105 superconducting transmon qubits, which are 5 times more coherent than those in Google's previous Sycamore processor. Willow was fabricated in Google's new fabrication facility in Santa Barbara, one of only a few facilities custom built to make quantum processors. As reported in Nature, Willow is also important because it can achieve quantum error correction below the surface code threshold. But what does this mean? Well, a key challenge in quantum computing is that qubits are prone to errors due to environmental noise and other factors. For several years, Google has therefore been working on an error correction technique called surface code quantum computing. Here, a square lattice of physical qubits, known as a surface code, is combined into a virtual or logical qubit with a lower error rate. The more physical qubits that are used to create a logical qubit, the lower its error rate should be. However, as a surface code lattice gets bigger, there are also more opportunities for error. This means that if the error rate of the physical qubits is too high, making the lattice bigger actually makes performance worse. However, if the error rate of the physical qubits is sufficiently low, or what is known as below threshold, then in theory the error rate of a logical qubit should decrease exponentially as more physical qubits are used. Using Willow, Google tested ever larger arrays of physical qubits, scaling from a surface code grid of 3 by 3 physical qubits to 5 by 5 and then 7 by 7, and each time they were able to cut the error rate in half. And in doing so, they overcame a challenge that has existed since quantum error correction was introduced in 1995. As an aside, you may have noticed that the surface code grids contain more qubits than required to hold data. This is because additional qubits are needed for measurement, with, for example, the 7 by 7 surface code comprising 49 data qubits and 48 measurement qubits, making a total of 97. Google's achievements with Willow have major implications. Indeed, as Harmat Neven, founder and lead at Google Quantum AI, has explained, as the first system below threshold, this is the most convincing prototype for a scalable logical qubit built to date. It's a strong sign that useful, very large quantum computers can indeed be built. Willow brings us closer to running practical, commercially relevant algorithms that can't be replicated on conventional computers. To prove the point, Google has used Willow to run a benchmark called random circuit sampling, or RCS. Here, Willow performed a computation in under 5 minutes that would have taken one of today's fastest supercomputers 10 septillion years. That's 10 to the 25 years, a period of time far in excess of the age of the universe. In February 2025, Microsoft announced a new quantum processor called Majorana 1. For some time, Microsoft has been working to create qubits using a topological phase of matter that's not a solid, liquid, or gas, and in 2022 it demonstrated the necessary physics using particles called Majorana zero modes. The Majorana 1 implements the technology in a quantum processor where topoconductors, or topological superconductors, are used to create qubits that are more stable and easier to control than those based on other technologies. The Majorana 1 contains 8 topological qubits. However, Microsoft claims that the chip is designed to scale to 1 million qubits. And so, in theory, the Majorana 1 and its topological qubits present a route map for creating a quantum computer that could have commercial, real-world applications. Also in February 2025, Microsoft's work led the US Defense Advanced Research Projects Agency, or DARPA, to include it as one of 2 pioneers to move to the validation and co-design stage of a program called Underexplored Systems for Utility-Scale Quantum Computing, or US2QC. This forms part of DARPA's larger quantum benchmarking initiative, which aims to determine whether it's possible to build an industrially useful quantum computer much faster than conventional predictions. Specifically, the initiative is investigating if any quantum computing approach can achieve utility-scale operation where computational value exceeds cost by 2033. The other pioneer in the validation phase of the DARPA US2QC program is PsiQuantum. Here, the plan is to create utility-scale quantum computing using photonic qubits, as I've detailed in previous updates. Back in April 2024, PsiQuantum announced it was going to build a utility-scale photonic quantum computer in Australia by 2027. In February 2025, PsiQuantum announced Omega, a quantum computing photonic chipset purpose-built for utility-scale quantum computing. This is a mass-manufacturable platform with silicon photonics modules created by traditional lithography. Omega is being fabricated in a commercial semiconductor foundry, specifically GlobalFoundries in New York, and, according to PsiQuantum, is the first realization of an integrated photonic technology platform capable of the on-chip generation, manipulation, and detection of photonic qubits. Like most quantum computing technologies, PsiQuantum's photonic qubits need to be cooled to extremely low temperatures. So, alongside Omega, PsiQuantum has introduced a new cooling solution. This is closer in design to a data center server rack than the chandelier dilution refrigerators often used. PsiQuantum therefore now has the technology to manufacture and cool vast numbers of quantum chips. Work is still needed to improve performance, manufacturing yield, and to connect chips together across racks into large-scale multi-chip systems. But, as the PsiQuantum website claims, their technology offers the potential to create fault-tolerant quantum computers capable of running commercially useful algorithms. Back with Microsoft, in November 2024, another significant development was reported. For some time, Microsoft has backed many different qubit technologies, and as part of this approach, it's been working with Atom Computing, who build quantum hardware based on arrays of neutral atoms. Here, the spin of an atom's nucleus is used as a qubit, with neutral atoms optically trapped in a computational array where they are manipulated by lasers. Because the nucleus of an atom is insensitive to external noise, neutral atom qubits have much longer coherence times than can be achieved with other technologies. In addition, because the trapped atoms in neutral atom hardware are only microns apart, there is the potential for massive scalability. And indeed, in April 2025, atom computing's approach captured the attention of DARPA, who selected them to join the conceptual phase of their quantum benchmarking initiative. As reported in this paper, Atom Computing and Microsoft have used a quantum processor with 256 neutral atom qubits to perform a number of experiments. These included creating 28 logical qubits encoded onto 112 atoms that were used to perform computation and which had a lower error rate than the physical qubits. The team also managed to create and entangle 24 logical qubits encoded onto 48 atoms, which, according to Microsoft in November 2024, represented the highest number of entangled logical qubits on record. Entanglement is where qubits are linked and share the same quantum state, which facilitates parallel quantum computation. The logical qubits encoded on the atom computing hardware were created using Microsoft's own qubit virtualization system. As with the Google example discussed earlier, this creates logical qubits by combining physical qubits in order to perform quantum error correction. According to their November 2024 announcement, Microsoft and Atom Computing will be offering a new quantum machine with reliable logical qubits, and which couples Atom Computing's neutral atom hardware with Microsoft's qubit virtualization system. This is due for delivery in 2025, although at the time of making this video in July, there's been no announcement of its release. Finally, we get to IBM, who, for many years, have published a roadmap of future quantum computing milestones that they have consistently achieved. In June 2025, IBM released the latest version, which details a framework for delivering a large-scale, fault-tolerant quantum computer by 2029. This will be named IBM Quantum Starling and is expected to have 200 logical qubits. If we scroll down the page, we find a graphic that again illustrates how a logical qubit can be constructed from many physical qubits to make it more resilient against errors. And if you take one technical learning point from this video, it should be how important it's become to combine noisy physical qubits into more reliable logical qubits to create fault-tolerant quantum hardware. Indeed, how many physical qubits a quantum processor possesses is likely to become irrelevant. It's logical qubits that are really going to matter, which is probably why Starling is the first machine on IBM's roadmap without a listed physical qubit count. In support of its claims and plans, IBM has released two new research papers. The first is a 66-page document that describes the architecture for a fault-tolerant quantum computer that uses bivariate bicycle codes. And, if you're wondering, these are an alternative to the surface codes used by Google and others for error correction. However, for bivariate bicycle codes to work, very fast circuit noise decoders are required. And in IBM's second new paper, they introduce such a decoder which uses an algorithm called belief propagation. Okay, so we're now disappearing into technical jargon. But stay with me for a minute, as if IBM delivers on its ambition, then by 2029 its Starling quantum computer will be able to execute quantum circuits comprised of 100 million quantum gates. Quantum circuits are the equivalent of programs in conventional computing and are a sequence of quantum gates that perform quantum computation. To give some context, in 2025, IBM's current Nighthawk hardware is able to execute up to 5,000 quantum gates. So, by 2029, IBM's quantum Starling system is expected to be about 20,000 times more powerful than current state-of-the-art hardware. And, according to its roadmap, by 2033, IBM expect to have a quantum computer called BlueJ that will have 2,000 logical qubits and so be 10 times more powerful. But before then, even the IBM quantum Starling system would turn commercial quantum computing into a reality, and I would place a strong bet that IBM will deliver it on time. By the early 2030s, many companies are likely to be using fault-tolerant quantum computers. Applications are likely to include molecular modelling, which will assist with the discovery of new medications, as well as the development of new construction materials and improved batteries. Logistics optimization, financial modelling, cryptography, and AI are also expected to be on the list of early quantum computing applications. And, almost certainly, most companies will access quantum hardware online, with several cloud providers already offering quantum computing as a service, or QCaaS. In the summer of 2026, I look forward to making my 10th quantum computing annual update, which will be a moment for significant reflection. But now that's it for another video. If you've enjoyed what you've seen here, please press that like button. If you haven't subscribed, please subscribe. And I hope to talk to you again very soon.